Hello everybody, and we will start with the quiz. Now we will try to answer these questions. The first question was, if a differential equation has a solution, it has infinitely many solutions, is it true or false? So Misha Zhukov thought that it is true. Is it really true? A differential equation must have infinitely many solutions. Okay, of course not, no, so there may be different kinds of differential equations, and not all have infinitely many solutions. We may consider, for example, an equation like, so I will use this space. For example, y squared plus y prime squared equals 0. So it is possible, this is a first order differential equation, but this is possible only, this equation is satisfied only for the function which is identical 0. The constant function, it is equal to 0 identically. So only this function satisfies this equation. So it is false. And this is the answer to the last question, number 5. Every first-order differential equation has a one-parameter family of solutions for its general equation, right? This equation has a unique solution, just one function, not a one-parameter family, not infinitely many solutions. The question?
Yep. Is there any differential equations with a non-trivial answer which have only one solution?
Non-trivial, okay, non-trivial answer. So there are examples of differential equations with no answer. For example, if it is equal to -1, then no answer. A trivial answer, right? But I think if it has not infinitely many solutions, then it has, if a differential equation has a unique solution, then it is almost trivial. So maybe something like, just a moment. Y minus x, maybe y minus x squared plus y prime minus 1 squared equals 0, for example. So the solution will be y equals x. So it is maybe non-trivial, but it is almost trivial, right? So usually we will not study these equations, but you should know that they exist, right? And the answer for the last question is false. It's false. Because there are first-order differential equations like this that have a unique solution or no solutions, or we have discussed the equation on the preceding lecture. We have discussed an equation y prime equals y minus 1 over x, which has two one-parameter families of solutions. So two one-parameter families of functions for their solution. So the first one-parameter family is c1 x squared plus 1 if x is less than 0, and y equals c2 x squared plus 1 if x is greater than 0. And if we consider, if we improve the equation, so let it be y minus 1 over x if x is not 0, and 0 for x equals 0. then we can join these two families. We may start with this series, with this integral curve, and then after the point 0, 1, we may choose another way with the constant C2, right? And so we have two one-parameter families of solutions. Okay. So you should be aware of some strange differential equations with not unique one-parameter family of solutions, with a unique solution, right? Usually they are not considered, but they are. They exist, right? So the second question, the equation y2 prime. So the third derivative of y3 primes plus 2 e to x times y prime minus 3y squared equals y3 primes is the third order differential equation. It is false. It was discussed during the first lecture on the differential equations. Right, it is false because we can cancel out the third derivative of y. It is not really involved in our equation, right? It can be cancelled out, so it is false. So question number 3. Two distant isoclines for a differential equation may intersect. So you should remember what it is. So what is an isocline for a differential equation? So should I recall this? Okay, so an isocline for a differential equation of the form y prime equals f capital of xy is a curve given by the equation f of xy equals k for some k fixed. K is a constant, it is fixed. And then this is a curve. It is some curve such that the slopes of the integral curves when they intersect this isocline are equal to k. So this is the curve with the constant slopes. For example, it's this. So that if the slope is equal to 1, right, we can draw this curve. It is an isocline with a slope 1 if k equals 1. So it is not possible for two isoclines for two different values k1 and k2 to intersect. K2. So because we have two different inclinations or slopes of them, so along these two curves, and if k1 is not equal to k2, then at the point of intersection, if it exists, we will have two different slopes. It is impossible, of course. So this contradicts the definition of an isocline. So you should remember the definition. Okay, next. If a point is not, okay, so it's false. So may intersect, right? It's false. If a point is not an ordinary point of a differential equation, then it is a singular point. Is it true or false? What is your opinion? So it is also false. So all the answers are false. It's also false, right? Because by definition of a singular point, let's recall the definitions. What is an ordinary point? Of a differential equation? So an ordinary point of a differential equation lies on one and only one integral curve. So there exists a unique integral curve that goes through this point. So this is an ordinary point, but a singular point, a singular point. Ordinary point, a singular point. Okay. A singular point must meet two requirements. So the first requirement, it is not an ordinary point, not an ordinary point. This means that if we consider this point a singular point, that it may lie on many more than one integral curve, or maybe there are no integral curves that go through this point, right? But there is the second requirement. It should be a limit point of ordinary points. It cannot be extraneous points. So this means that for infinitely small, so if we consider a circle with an arbitrary radius, infinitely small, so it may be arbitrary small radius, such that there is an ordinary point inside this circle. So a singular point should be a limit point for ordinary points. And you should not forget about this second requirement. So it's also false. So all the answers are false. And now we will try to solve the differential equation. Let's solve this differential equation. Okay, first of all, we should put this differential equation in the standard form. So it should be y prime minus 4 over x y equals to x. Okay. Now look at the coefficient at y. This is the, so first of all, what is the type of this equation? It's the first order linear differential equation. Linear, it is linear in y prime and y. They are both raised to the first power, right? The exponents of these two functions is 1, right? Then look at this coefficient, minus 4 over x, call it a. Okay. Then we should compute u of x will be, so first we will integrate. So first let's integrate, is equal to the integral of minus 4 over x dx equals minus 4 ln absolute value of x plus c, but we need to know c. And then u of x is a multiplying factor. It will be equal to e raised to minus 4 ln absolute value of x. It is x raised to the power minus 4, and it is equal to 1 over x to 4. So it will be the integrating factor, and then if we multiply both parts of our equation by this factor, we can represent the left-hand part as the derivative of u of x times y. Okay, just it will be y divided by x to 4 prime. It is y prime divided by x to 4 minus 4y divided by x to 5. Okay. And so this brings our equation to the following one. U of x will be, so y over x to 4 prime is equal to 2x divided by x to 4. So I recall the idea. We considered our differential equation, and given an integrating factor, we should multiply both parts by 1 over x to 4. On the left-hand side, we will get the derivative of this function, and we will get 2x over x to 4 on the right-hand side. Right? And then y over x to 4 is equal to the integral of this, so 2 over x cubed dx. It is equal to 2 times x to negative 2 over negative 2 plus c. It is minus 1 over x squared plus c. And then after this, we can conclude that y is equal to minus 1 over x squared plus c times x to 4. And we can expand this, and we will get the final answer, x squared minus x squared plus cx to 4. So, Misha, your answer is correct. And what about you? Follow, and Kathy? No? And Kathy? Right. So this is the quiz. And now we will move on to our lecture. So today we will consider exact differential equations. Exact differential equations. The method of solving exact differential equations, and I prove the theorem that gives the method of solving. And if we have time, we will consider the method of integrating factor. Okay, so today we will consider the new type of differential equations. They are still first order differential equations. They are called exact differential equations. Okay, before beginning a study of this type of differential equations, we will review some facts from calculus, from theory of integration, that we will need later, right? So the first fact, I will use this space. First, if we want to integrate, so given a continuous function, let f of x be a continuous function. So is a continuous function. Given on some interval, so x is between a and b. And let's consider the new function f capital of x, which is equal to the integral of f of x dx from a. So to be precise, this is a new variable, t. Let it be t, dt. So what can we say about this function? If f of x is defined as this definite integral from a to x of f of t dt, what is the derivative of this function, f prime of x? what is it equal to? F small of t, right, of x, right, by the fundamental theorem of calculus. It is the fundamental theorem of calculus. If f small of x is continuous, then it is true. Right. Okay, so today we will integrate, and sometimes I will use, to be precise, this should be some variable t, and this is the upper limit of integration, it is x. But to simplify my computations, sometimes I will use the following. I will write f of x equals the integral from a to x of f of x dx. So I will do this because we'll have so many functions, notations, and variables. So it would be more convenient to use this, maybe not correct, but I think it is not confusing because all of us know what is going on, and so I think it should be not confusing. Okay, this is the first fact I wanted to speak about, and the second fact was about the functions of two variables. And suppose we want to consider the integral. So given two functions, p of xy and q of xy, that are continuous and that have their common domain of definition. So they are defined on the common region or on the common domain. So are defined in the common domain, let it be D. Okay. And I want to consider the integral, the following integrals. So I will integrate p of xy from x0 to x. And I want to integrate q of x from y0 to y. I want to know when this operation is defined, is well defined. Okay, so we are given a point x0, y0. So the first requirement is that x0, y0 is a point in this domain D. So both functions should be defined at this point. And so suppose this is our domain. Okay. Next, I want to integrate p of xy along the segment from x0 to x, keeping y fixed. So suppose y is fixed. Let's integrate. Okay. So this is my segment. It is x, y0. Okay, and this is the second segment. It is x0y. So to be able to find this both integrals, I should require that the rectangle determined by these line segments joining these pairs of points is contained entirely in our domain. Right. And not only the sides of this rectangle, right, but all them interior points. Because, for example, look at this first integral. Y is fixed, and we need to integrate from x0 to x. So this means that I should be able to integrate along any horizontal line, right? and our function must be defined at any point in the interior of this rectangle. And the same is true for the second integral. So because I integrate along any vertical line given x fixed, keeping x fixed, and so I require that our domain is I require that the domain be a simply connected domain, right? It is so I will give a definition. The domain. So a domain D is called as simply connected it's called simply connected, just let it be simply connected. If every simple closed curve lying entirely in D encloses only points encloses only points in the domain. From the domain, let it be from the domain. So this means the following. What is a simple closed curve? Any simple closed curve. What does it mean? Simple closed curve. Do you know? Closed. So is this curve closed or not? No, it is not closed. Closed means that it is enclosed in some region, right? So the endpoint, the endpoints of this curve should coincide. So this curve is closed and this is not. And what about simple curve? Simple.
No intersection.
Well, no intersection, right. So this curve is not simple. Right. So this is a simple closed curve. So it must enclose only points from the region. This means that our domain should not have any holes inside it, without holes. So, for example, this domain with a hole inside is not a simply connected domain. It is not a simply connected domain. Is it clear? So the definition is clear, right? Or simply connected region, simply connected domain, so it's the same, right? Well, and so we will require, so we will consider the integrals of this type, and we will require that our region be simply connected, and the point x0, y0 is the point, so it is contained in our domain, and rectangles with the so the rectangles determined by the closed segments joining the points, so x0, y0 with x0, y, this is the first side, the second side joining x0, y0 with x, y0, it should lie entirely in our domain, right? So these are our requirements. And now let's move on to our exact differential equations. So I will start with the example. Just a moment. Well, let's consider a function. Okay, let it be maybe x cubed minus 2xy squared plus y. Okay, I think it's enough. So let it be this. It is defined on the entire plane. So this function is defined for any point xy from R2. Okay, and let's consider its differential, its total differential, df. So to find df, we should first find the partial derivative of this function with respect to x, keeping y fixed. Right, so y is fixed, and let's differentiate with respect to x, and we will get 3x squared minus 2y squared. Then dx plus. After this, we need to differentiate with respect to y, keeping x fixed. And we will get minus 4xy plus 1 dy. So this is a total differential. Okay. So I will denote this function by p of xy, and this is by q of xy. And suppose we want to solve the following differential equation. Let's solve the equation 3x squared minus 2y squared dx minus so plus 4xy plus 1 dy equals 0. Is it possible to solve this differential equation? But since we know that this is the total differential of our function f, so let it be df of xy, then we can see that this is the same as the equation f of xy, df of xy equals 0. Okay. And so the solution will be f of xy is equal to the constant. And so given this equation, we know that the solution will be x cubed minus 2xy squared plus y equals c, where c stands for an arbitrary constant. So this is a solution to this differential equation. Okay. But we knew in advance that we knew the function in advance. But sometimes we want to solve the equation. So I will use this space. P of xy dx plus q of xy dy equals 0. And I claim that if we know that there is a function such that this is a total differential of this function, then we can easily solve this differential equation. Okay. And now, so I need to introduce some definitions, some notions. So it will be definition number 2. So the expression p of xy dx plus q of xy dy is called an exact in exact differential, if it is a differential, it is a total differential of some function, okay. Okay, and the equation, so the differential equation p of xy dx plus q of xy dy equals 0 is called the exact differential equation. If there is a function f of xy such that df is equal to p dx plus q dy. So this is the definition of the exact differential equation. So in our example, we knew in advance that this is an exact differential and this is an exact differential equation. And so it is easy to find the solution. But sometimes, if the differential equation was selected at random, then two questions would arise in this situation. The first question, how would we know that the differential equation was exact? How to check that it is exact? So given the functions p and q defined on the common simply connected domain, we want to check, to know the method how to check if it is exact or not. And the second question, if the equation were exact, how to find the solution?
Well, if it's an exact differential, then the derivative of p with respect to y is equal to the partial derivative of q
with respect to x. Right. So this is the answer. Right. This will be stated in the theorem. So we will add some additional requirements to impose some conditions of on the functions p and q. They should be continuous, and their partial derivatives should be continuous, and the domain should be simply connected. And in this case, you are absolutely right. So this is the condition for the necessary and sufficient condition for this equation to be exact differential equation, right? And so our theorem, now I will formulate, I will state and prove the following theorem, and this theorem will answer both questions: how to check if our differential equation is exact, and how to find the function which will give us the solution to this differential equation. So I will write the theorem here. Misha, did you know this in advance, or right? In physics, right? I see. And you, Misha?
Well,
you too?
For preparation for the quiz, I was studying it.
You're right, I see. Okay, so there will be a theorem. So necessary Okay, for the equation p of x y dx plus q of x y dy equals 0 to be exact, is that, so the main condition is that the partial derivative of p with respect to y, dp over dy, should be equal to partial derivative of q with respect to x. So these partial derivatives should coincide, where the functions p of xy, q of xy, their partial derivatives, so dp over dx, dp over dy, okay, I think dp over dy only, I think we will not need. So dp over dy, dq over dx are defined and continuous in a simply connected region. Okay, and so now I will prove this theorem. So, but this theorem is so it is valid as stated, right, for a simply connected region. But I will prove it for the rectangular region contained in a simply connected domain, right? So for some more simple requirements, maybe more. Okay. Bye. Right. Let's give a proof of this theorem. So first, we will start with the necessary condition. Necessary condition. I think it is not difficult. So this is the easiest part of this. So there are two parts: necessary condition. So we will prove that it is necessary condition and sufficient condition. So this is the so the first part is of course more easy than the second one, right? It's the easy part of our theorem. So if we know that there exists a function such that df is equal to p dx plus q dy, then we know that p is equal to the partial derivative of f with respect to x, and q is a partial derivative of f with respect to y. Okay. What about mixed partials? d to f, dx, dy, and d to f, dy, dx. Are they equal or not? Okay, so for continuous, right. If these derivatives are continuous, then by Young's theorem they are equal. Right? Not always. There are some counterexamples when this is not satisfied. So we know that these partials, so dp over dy and dq over dx, are continuous, and so for this situation they are equal. So by Young's theorem. Okay. Right. So this is proved. This part is proved. And now let's prove sufficient condition, right? That it is sufficient. Okay, so given this, we want to prove that there exists a function such that p is a partial derivative of f with respect to x, and q is a partial derivative of f with respect to y. And this proof will give a way how to construct this function, how to find it. So we will answer the second question also. We will not only prove that this function exists, but we will find the formula for this function. And this will give us the method of solving the exact differential equations. Right? Okay, so we want to find the function f of xy such that df over dx equals p. Okay, so let's fix y. If we fix y with y constant, we will try to integrate. So let it be, so f of xy, we will start with some point x0 lying in our domain, right, to x, p of xy dx. Okay, and this will include some constant. Let it be a constant f of y. Okay, so this will denote the constant, right? Let it be so f, right? Let it be f. F capital, or maybe let it be r. Maybe let's use another letter for the constant. R of y is some function depending only on y, but not on x. Okay. So if we fix y, we can check that then the partial derivative of f with respect to x will be p of xy, right? So if we differentiate, okay, look here. So this is that the situation that was described in the beginning of our lecture, right? More precise. So it would be more precise to use some other variable t maybe, right? Because this is the upper limit of integration x. But it's better to use another variable instead of x. But maybe I will use x, and I hope that it will not cause confusion, right? Let it be x. It is more convenient, just more convenient, right? So this is f. Now we want, so this is the first step. Just a moment, let it be the first step. Next, step number 2. We want that the partial derivative of f with respect to y is equal to q, right? We are looking for the function such that its partial derivative with respect to y is equal to q. Q is a given function. Let's find the partial derivative of the function given by this formula with respect to y. Let's differentiate this with respect to y. So what is df over dy? It is equal to d over dy, and we will integrate the differentiate the integral. It will be p of xy dx plus r prime of y. Okay. Okay, I want to continue this. So can we put this partial differentiation inside inside the integral sign. Can we move it to the function p or not? Do you know? Not always, but now we can do this because we are given that dp over dy is continuous. If it is continuous, then it is possible, it is correct. And now we will do this. It is equal to the integral d over dy p of xy dx plus r prime of y. Okay. What about this? So we are given that this is so we are trying to prove the sufficient condition. So this means that we are given that this is satisfied, right? This is satisfied. And then we want to prove that our equation is exact. So we can use this, right? So we know that dp over dy is equal to dq over dx. And we will use these facts. By the hypothesis, it is equal to d over dx q of xy. Let's substitute this for the given expression. Let's consider this integral more closely. So, given y fixed, with y fixed, first we find the partial derivative of q with respect to x, and then we integrate this partial derivative with respect to x also. With y still fixed. So, under these two operations, y is fixed. So if we integrate the derivative, then it is equal to what? It is equal to q of xy minus q of x0y plus r prime of y. Okay, and so now we want df over dy to be equal to q of xy. We want this. We have found df over dy. We know that df, so I will rewrite this. The result is df over dy equals q of xy minus q of x0y plus r prime of y, and this must be equal to q of xy. Q of xy. Okay. So, is it possible to satisfy this condition or not? What is your opinion? We are looking for the function such that, so df over dy is this, and it must be equal to q of xy. Is it possible to satisfy this equation or not? So, okay. We can cancel out this same terms from the left hand side and the right hand side, all right? You can see q of xy on the left hand side and q of xy on the right. We can cancel them out. Okay, and we are left with the equation r prime of y equals q of x0y. This is a derivative with respect to y, because r is the function depending on y only, so prime means the derivative with respect to y. So is it possible to find r of y? Can we find it from this equation? Of course, yes. So just integrate both parts, right? So this means that r of y is equal to the integral from, so we should integrate with respect to y. So from y, 0 to y, q of x 0y dy. Okay. Now let's summarize our results. So we have started with the function given by this equation, and we have found the expression for r of y. Let's gather these two formulas together, and I will write the answer. I will use this space. Okay, then if we define f of xy to be the function defined by this formula, the integral from x0 to x of p of xy dx plus the integral from y0 to y q of x0y dy. Okay. Okay, is it clear? Now we have replaced r of y by the formula obtained on the second step, right? And so this is the answer for the function. Okay, so the result is, given this, if the partial derivative, the partials, right, the partial derivative of p with respect to y equals the partial derivative of q with respect to x, then we can find the function using this formula. And so this will give the answer to both questions. So we know that our equation is exact, and we know the function, so we can solve this exact differential equation. How to solve it? The solution will be given by the solution will be the integral from x0 to x p of xy dx plus the integral from y0 to y q of x0y dy equals the constant, a constant, right, some arbitrary constant. So this will be the solution to the exact differential equation. And now, so the last step is to check that this is actually a solution. So let's check that the differential of our function is exactly what is given. So this is the differential of our function. So we may check that, but the steps to check it are similar to our proof, but maybe let's do this. Let's step number 3. Let's verify that the function given by this formula is actually the function such that, so let's check that the differential of f is equal to p dx plus q dy. Okay. But I think it's an easy exercise, right? Okay, I think I can leave it to you, right? Can you check this? So you should check this. Will it be an easy exercise? Okay, now on the seminar we will use this formula to solve exact differential equation. And so I'd like to to complete our lecture with maybe 2 remarks. So the first remark is, okay, we can in our proof, and so to construct our formula, we have started with the equation df over dx equals p of xy. But we may start with the other equation, df over dy equals q of xy. And had we started with this equation, we will give the formula which is slightly different from our obtained here. So it will be, so had we started with this, the formula were the formula would be the following. It would be the integral from y0 to y, q of xy dy, plus the integral from x0 to x, p of x y0 dx. Right? So they are 2 formulas, but both will lead to the same function, of course. And so in hand computations, so if we want to solve their concrete examples, we may use any formula, the easy formula, right? We may use the easiest way to solve the equation, and so we may compare maybe in our mind which formula is more easy to apply and use this formula. Well, so this is the first remark. Right. Okay, and the second remark is the following. So this is the formula. It is very easy. It looks easy. And so now it is written, and I will show you that the process of solving differential equation with this formula is very easy. And so this is the advantage of this formula. It looks easy, and it is easy to to use, but the disadvantage that it is it can be forgotten, easily forgotten. But if you remember the process of obtaining this formula, you will be able to solve any differential equation, exact differential equation. So I will show you 2 ways how to use this formula